Shall we start?
Yeah.
So today we are very glad to have Xinan Zhou from Princeton Center for Theoretical Sciences, who will tell us about an analytic bootstrap approach for CFTs on RPD and CFTs with boundaries. Please.
Okay, so thanks a lot for the introduction, and thanks very much for the invitation to give this talk. It's a great pleasure to be in Harvard, although only virtually. So today I'm going to talk about CFTs on real projective space, and also CFTs with boundaries. And the talk is based on two papers with my great collaborators, Simone Giombi, Himanshu Kanchandani, and Dadimir Mazach and Leonardo Rastelli. So the real projective case was discussed in this paper from this year, and the boundary case was discussed in an earlier paper. Okay, so let me start my talk with some general motivation. So as I already mentioned, we are going to consider theories on two types of manifolds. The first is a space with a boundary, and more specifically, we are going to consider the boundary being a codimension one plane or a sphere. The second case is a real projective space. The case with boundaries is easy to motivate because in real life, systems they are of finite size and they always have some boundaries. And at critical points, the presence of boundaries leads to interesting surface critical behavior, which is described by boundary CFTs. The case of real projective space is less familiar, but they also show up, for example, in string theory. So the worldsheet CFTs include cases with both boundaries and also cross-cup insertions, and a cross-cup is just a two-dimensional real projective space. And more generally, it is an interesting theoretical question to ask how CFTs are formulated on manifolds which are not conformally equivalent to RD. For example, on manifolds which are not orientable. And the simplest non-orientable manifold in even dimensions is a real projective space. Now, studying theories on real projective space is not just some theoretical interest, but it also has practical uses. So by placing the theory on real project space, we can, for example, probe the realization of time reversal symmetry, which has applications in interesting condensed matter problems. On the other hand, in recent years, we know the conformal bootstrap method has become a very powerful tool for non-potentially studying the physics of CFTs. And in the numerical bootstrap, the usual setup is in RD. And now by considering theories with boundaries and on real project space, this is going to pose some interesting challenges for the usual bootstrap techniques. So in the last slide, maybe you were wondering why I put the case of boundaries and real projective space next to each other. And it turned out we are soon going to see that this is a very natural thing to do because these two cases, they have a lot in common. For example, in both cases, the conformal symmetry is partially broken. And we also have more observables in these theories than in the theory defined on RD. For example, in both cases, we can have non-zero one-point functions, and the coefficient of these one-point functions encode extra theory data. Also, in these examples, the two-point functions now replace the four-point functions of CFT in RD to become the simplest non-trivial correlators. And here by non-trivial, I mean the correlator is not determined just by conformal symmetry. And the kinematics of 2-point functions is much simpler than that of the 4-point functions. So that makes the 2-point functions the ideal playground for experimenting with new analytic techniques. And that leads to the goal of today's talk, which is just to introduce some non-perturbative analytic bootstrap methods to study 2-point functions in these systems. So here is an outline of the plan of today's talk. So I'm going to now review some basic kinematics of boundary CFTs and CFTs on real projective space, just to set up the stage. And then I'm going to introduce an analytic approach to study 2-point functions of RPD CFTs. And there's a similar approach for BCFT 2-point functions, but I'm only going to sketch the main ideas and emphasize the differences. And finally, I'm going to conclude with some future directions. So, and please stop me if you have a question or something is unclear at any point of the talk. Okay, so let's start with the general setup so that we are on the same page. So first, real projective space of d dimensions can be defined by taking a d-dimensional sphere, and then we identify the points which are antipodal. So we can just take the northern hemisphere of this d-dimensional sphere. In practice, it's more convenient to not work with these sphere coordinates. So we can perform a conformal transformation and map this into RD. So the northern hemisphere is mapped to this disk here of unit radius. And the southern hemisphere is mapped to the rest of the space. And this identification, which identifies antipodal points, has now become an inversion with respect to this unit sphere. And a point inside this disk is identified with another point outside of disk. The boundary case is simpler. We just take the northern hemisphere. And we can also do a conformal transformation to map this into a disk in RD, or we can do another conformal transformation to map this into half space. Now, the presence of boundary and doing the quotient is going to partially break the conformal symmetry as follows. And there are many ways to see how this happens, but in the following, we are going to see it by using the embedding space formalism, which will become useful in the next few slides, because this formalism allows us to linearize the action of the conformal group. So let's first consider a case where we don't have any boundary or quotient. Then each point in RD is now represented by a null ray in the embedding space that has 2 more dimensions. And these 2 more dimensions, one of them is time-like. So here, by now, I mean P times P is 0. And also, it's a ray, so we can identify points which are related by overall scaling. Now, we can choose a particular rescaling such that the coordinates in the embedding space is of this form, where the first component is time-like and the other components are space-like. And in the embedding space, the conformal group acts just as a rotation in this D plus 2-dimensional space. A generic rotation is going to take us away from this choice of rescaling, but we can always do another rescaling to bring it back to this form. And by comparing these components, we can read off how the conformal transformation acts on these RD coordinates. So that's the case where we don't have a boundary or a quotient. Now, if we introduce the quotient and the boundary, that correspond to introducing some fixed vectors. So in the RPD case, we are going to introduce a fixed vector NC, which has components 1, 0, 0, and so on. And the inversion we saw earlier can be expressed in terms of this fixed vector as follows. And similarly, in the boundary case, it amounts to introduce a fixed vector whose first two components are just swapped. And here, the boundary is described by all the points in the embedding space which satisfy p times this fixed vector equals to 0. So introducing these vectors apparently breaks the rotation symmetry to a subgroup which preserves these fixed vectors. So that's how we see the symmetry is broken to these subgroups. And also the breaking of the conformal symmetry allows more observables. For example, scalar operators can now have non-trivial one-point functions. And because we still have Lorentz symmetry, so only scalar operators can have one-point functions. In the embedding space formalism, operators are defined on these null rays we saw in the last slide. Because we can scale these rays, so the operators should also have proper scaling behavior under rescaling the coordinates. So the behavior is as follows. We have an overall power. Now we can consider one-point functions. The one-point functions need to satisfy two constraints. The first is that it needs to be invariant under the rotations that keep the fixed vectors fixed. And the second is that the correlation function of this operator must scale according to this. And the only choice we have is to consider the scalar product of the fixed vector times the coordinate p and raised to some power minus delta. We can express this in terms of the RD coordinates, and we find that these one-point functions their position dependence is completely fixed by conformal symmetry, but the overall scaling is not fixed. And these overall coefficients, these A's, are new CFT data, which were not present in the RD case. And here is a very minor comment. So in the RPD case, we are identifying the operators which are related by inversion. And then there's then a choice we have for the overall sign. We can choose either plus or minus. And it's only for the plus choice that one-point function is non-zero. And the reason is that under this Z2, the total charge must be 0. So that was the one-point function, which is completely fixed by symmetry. Now let's go to two-point function. And in this case, it's more interesting because we can now construct a cross ratio, which is invariant both under conformal symmetry and scalings. So the cross ratio is constructed by taking P1 times P2, which are the coordinates of operator 1 and 2, and divided by the fixed vector times P1 and the fixed vector times P2. Now, in terms of these cross ratios, we can write the two-point function as follows. So we first take out the kinematic factor, which is just the product of two one-point functions. This part takes care of the scaling. And then the risk dependence is a function of the cross ratio, which a priori can be anything. And here we want to compare this to a CFT four-point function with space and dimension d greater than or equal to 2. So in the four-point function case, we have two independent cross ratios, but in the two-point function case, we have just one. So that makes these two-point functions much simpler to study. Now let me point out some interesting limits which we can take. And some of these limits are related to the operator product expansion. So we first start with the BCFT case. Here I wrote down again the cross ratio. So the first interesting limit is when Kc goes to 0. So that happens when these two operators are close to each other. This allows us to use the standard OPE to write the product of two operators as the linear combination of operators. And this also gives us a way to compute these 2-point functions. So we can just take the expectation values on both sides. And this reduces the 2-point function to a sum of 1-point functions. Now, because we still have Lorentz symmetry, so only scalar operators can have 1-point function. So so in this way of computing 2-point functions and 1-point functions, only scalar operators can be exchanged. The contribution of exchanging a primary operator and together with its descendants can be summed into a conformal block, which is just on 2f1 function. And we are going to call this channel the bulk channel. The second interesting limit is when Kc goes to infinity. That corresponds to operators taken close to the boundary. And there's a different kind of OPE where a bulk operator is expressed as a linear combination of operators which live on the boundary. Now we can do this for both operators, and then we have another way of computing the 2-point function, which is to express it as an infinite sum of 2-point functions on the which lives on the boundary. And again, because of Lorentz symmetry, only scalar operators can appear. And the contribution of each exchange operator is captured by a conformal block. And this channel is called the boundary channel. Now, these two different ways of computing the 2-point function must agree with each other. So we have the following equation known as the crossing equation. So on the left, we are decomposing the 2-point function in terms of bulk channel conformal blocks. And in the right, we are decomposing the 2-point function as boundary channel conformal blocks. The coefficients of each conformal block is related to the 3-point OPE coefficients and a 1-point coefficient. So on the in the bulk channel, this mu I is just the 3-point function times 1-point function, while in the boundary channel, it's just the square of 1-point function. If the theory is unitary, then all these numbers are real. So we can see that these mu hat, they are positive. But for the bulk channel, these mu i's, there is no constraint on the sign of this quantity. So this crossing equation, it's not trivial to satisfy, and therefore it imposes constraints on the CFD data. So this is very similar to the 4-point function case. But on the other hand, we noticed here that in the bulk channel, these mu I, they don't need to be positive numbers. That means the standard numerical bootstrap for 4-point functions no longer applies here, because that relies on the positivity in each channel. There is an alternative introduced by Gliozzi. The idea is just to truncate this crossing equation in the expansion of the cross ratio to a certain order, and also you truncate the spectrum. And then you solve this truncated crossing equation and get some approximate estimate for the CFD data. But this method is not a rigorous method because the systematic error in this truncation cannot be controlled. And finally, there is another interesting limit where this cross ratio Kc goes to -1. And this limit is not possible in the Euclidean signature. We can only reach that after we analytically continue this to the Lorentzian spacetime. And physically, it means that one operator is approaching the light cone of the image of the other operator. And this limit can be thought of as a ridge limit. It's very similar to the ridge limit of 4-point functions in RD. And if the theory is unitary, actually we can use the positivity of the boundary channel to prove that the correlator must be bounded in this ridge limit. And it should not grow faster than this power here. Now let's go to the projective space. The cross ratio here is given by this eta, and the first interesting limit is when eta goes to 0. That corresponds to two operators being close to each other. So we can use the standard OPE again and decompose the 2-point function into conformal blocks. And again, there are only scalar operators involved because we have Lorentz symmetry. The second interesting limit is when eta goes to -1. And that is the limit when one operator is approaching the inversion image of the other operator. Now, since operators are identified under inversion, so this limit is essentially the same as the first limit. And more specifically, the inversion maps the cross ratio from eta to 1 minus eta, and that gives us the conformal block in this mirror channel, which I denote here with an extra bar. So G bar eta is G at 1 minus eta. Now, these two different ways of computing the 2-point function should again agree, and it gives us the following crossing equation. And this coefficient in front of each conformal block is the product of a 3-point OPE coefficient and a 1-point coefficient. And this plus minus correspond to the common choice of plus minus for operator 1 and 2. And again, I want to emphasize that these coefficients don't need to be positive. So the standard techniques of numerical bootstrap does not apply here as well. And similar to the BCFT case, there's also a third limit that's interesting. And here, so there it was called the ridge limit. And here we want to identify it with the limit where eta goes to infinity. And it is also a limit that's only possible in the Lorentzian signature. The difference is that in the RPD case, we don't have a boundary channel anymore. So we never have positive coefficients. So we cannot use unitarity to prove the bounded behavior of the correlator in this limit. So just to summarize this part, the final comment is that we see that the kinematics of BCFT and RPD CFT are very similar. And very formally, we can even consider these two as being related by analytic continuation, where we replace x squared with minus x squared. And this will immediately relate these two different cross ratios. And also, it shows that the bulk channel conformal block in the BCFT case is the same as the conformal block in the RPD case. And of course, there are differences. For example, there's no boundary channel for the RPD CFT. So maybe I should pause here for a second to see if there are any questions.
Yes, can I ask something? Can you explain again the OPE in the original projective plane? And do you have to have two operators or just one? That
yes,
how does this work?
Yeah, I do need to have two operators. So in this case, I'm just doing the standard OPE, and I'm trading two operators with the linear combination of operators, single operators.
No, but the other one that looks like a boundary.
Right, right. So this this point is the inversion image of the other operators, which I'm keeping to be fixed. And now I'm moving the other operator. So if the other operator goes to this operator, it's the eta goes to 0 channel. But if it moves to the image of this operator in this picture, then it's the eta goes to -1 limit.
But I don't understand. But the white region is identified with some point in the blue region, right?
Yes.
So what? So in principle, you can tell this story only in the blue region. So I don't understand where is the second operator.
Well, right. So I guess you can see it from here. So these conformal blocks, they are not, they don't obey this identification. So they are not invariant on the eta goes to 1 minus eta. So it's only the final answer, the 2-point function, is invariant under eta goes to 1 minus eta under this identification. But for this individual building block, it's not. So this is really before we take this quotient. So so we are just imagine that we are on a d-dimensional sphere, and we have an operator and also the antipodal points of that operator. And then there are two limits we can take.
Does it have to happen on the unit circle, like 2 points on the unit circle, which are antipodal?
Sorry, what do you mean on the unit circle? These points are not on the unit circle.
No, but the limit that is like the boundary limit. That is
sorry. There is no boundary. Yeah, I should emphasize that there is no fixed point under this inversion. So if we take a point here on the boundary of this disk, it's mapped to the antipodal point on the upside.
Yeah, sure. So okay, I'll think about it.
Okay, yeah, we can. Sorry, I'm not sure if I answered the question, but we can talk more later. Okay, any other questions?
Excuse me. For
Yes.
RPD, when D is even is unorientable, but
Right.
for D is odd is orientable.
Yes.
Are there some special case of dimension you will consider, or you will apply to any dimension?
Yeah, so this fact of being orientable or not is not important to us. So here we are just going to keep D general. And actually, even we are going to take D to be like some fractional number when we consider like something like 4 minus epsilon expansion.
And is there a reason you want to consider RPD instead of other manifold? Maybe say RPM times some sphere or some other space.
Yeah, these are certainly very interesting, but they are more difficult compared to this case. So here we just want to look at the simplest such manifold.
Okay, no problem. Thank you.
Thanks. Any further questions before we move on to the next part? Okay, so let me continue. So so because the rest of the talk is a bit technical, so I want to first outline the main goals and the logic of the rest of the talk before we get lost in the details. So as I showed you in the previous slides, that these 2-point functions, they need to obey these crossing equations, which contain constraints on the CFT data. And in the talk, we are going to view these crossing equations as some sort of vector equations living in some space that is infinite dimensional. So this space is the space of functions, and I'm going to denote it by this V here. So the first question is, what is a basis for this vector space V? So so one of the goal of today's talk is going to introduce a new useful basis for this space. And this new basis is going to be different from the conformal block decomposition we saw in the previous slides. And this new basis, instead of being a continuous basis where the conformal dimension takes continuous values, it's going to be a discrete basis. Now, once we have defined such a new basis, we can define a dual basis for the dual space V star. And this V star is just the space of linear functionals. And we can require that this dual basis of V star acts on this basis of V in the also normal way. But this does not specify these dual bases. So we still need to know how these individual functional acts on a function in this space V. So to do that, it's sufficient to determine how these functionals act on a genetic conformal block, and the action is something which we are going to analytically construct in today's talk. Now, once we know these actions, these functionals are completely specified, and now we can use them. And the way to use them is to apply these functionals on these crossing equations. We apply that on both sides of the crossing equation, and that is going to turn these crossing equations into some rules about the CFT data. Now, this problem I outlined is completely kinematical and has nothing to do with the dynamics of any specific CFT. However, in today's talk, to solve this problem, we are going to take a holographic detour. But precisely what I mean by that is we are going to construct and study a seemingly irrelevant holographic toy model. But in this model, we are going to introduce a special class of functions, which are the Feynman diagrams in ADS. We don't really care about the physical meaning of these toy models, but what we do care about is the structure of these special functions under the conformal block decomposition. And we are going to see that the decomposition property of these Feynman diagrams is going to give us the natural basis for the space of functions. And moreover, for these dual bases, which are the functionals, we can construct all their actions by just reading off the decomposition coefficients from the decomposition of these Feynman diagrams. And in today's talk, I'm going to explain this construction in detail for the case of CFTs on real projective space. The BCFT story is largely similar, so I will only sketch the main idea. Before I move on, are there any questions about the main logic of the talk? Okay, so if there are no questions, I'll start with this construction. So the first step of doing that is to extend its quotient into ADS space. And to do that, it's also useful to use the embedding coordinates we used earlier. So to describe the ADS space, I'm going to use the Poincaré coordinates. It has radial coordinate z0, and this also RD coordinates z mu. And the metric is given by this. I think I missed the squared here, sorry. And this, so these coordinates, you can visualize it as a half space where the direction that goes up is z0, takes value from 0 to infinity. And then you have the other directions, which are rd. And we can rewrite these coordinates in terms of a d-dimension, d plus 2-dimensional embedding vector as follows. And these vectors, they satisfy the condition that z squared is -1. So here I've set the radius of ADS to be 1. Now, the inversion, which acts on the boundary coordinates, can be written in terms of the embedding coordinates as flipping the sign of each component except for the first one. And we can require the inversion act the same way on the ADS coordinates. So we just replace P with A. And then from the components, we can find that the following action. And geometrically, it just means we are doing an inversion with respect to a unit radius hemisphere located at the origin of the boundary. So a point inside of this sphere is identified with another another point z bar outside of the sphere. And notice that this map has a fixed point, which is the north pole of this hemisphere. And its embedding coordinate is nothing but the fixed vector NC we saw earlier. It's this fixed vector 1, 0, 0, 0, 0. So now we identify these points under inversion, and then we get a Z2 quotient of this ADS space. And of course, the boundary of this quotient ADS is just RPD, which is this gray slice here. And we are going to consider effective series that lives in this quotient space and study tree-level Feynman diagrams, which are also called Witten diagrams in the ADS context. So to do that, we need two ingredients. The first is propagators, and the second is vertices. So let's first start with the propagators. The propagators are very easy to compute. We can just use the method of images. So there are two types of propagators we care about. The first is the bulk-to-bulk propagator. It tells us how the field propagates from one bulk point to another bulk point. And the second is the bulk-to-boundary propagator, which tells us the propagation from the bulk point to a point that lives on the conformal boundary. And the method of images tells us these propagators can be written in terms of the propagators of ADS without quotient. So these functions G as the Green's function in the full ADS with no quotient being taken. And these G, they satisfy the following equation of motion, and the bulk-to-boundary propagator is just a simple power of these embedding coordinates. And the second ingredient is vertices. So in addition to the usual ADS vertices, for example, like cubic couplings that couples three fields together, like phi 1, phi 2, phi 3. And we also have another special type of vertices which are localized at the special point NC, which is a fixed point under inversion. So these are so this vertex takes the form of some field phi, but their coordinates is fixed to be NC, so they're localized. So these are the ingredients we need, and now we can use them to build Feynman diagrams. So the simplest diagram to write down is the one-point function diagram. So to do that, we just need a vertex of the special type, which is localized at the north pole. And this diagram tells us this one-point function is just given by a single bulk-to-boundary propagator. And there's no integration needed here. So when we write it out explicitly, we find indeed we get the form which is determined by conformal symmetry. So that's the one-point function. Let's now move on to two-point function. The two-point function, the simplest two-point function is given by a contact diagram where there is a contact interaction localized again at this north pole. So this diagram tells us that the two-point function is given by the product of two bulk-to-boundary propagators, or equivalently to one-point functions. And if we write in terms of cross ratio, this correlation function is just a constant. Now here in this vertex, I did not including any constructed derivatives. We can also do it more generally by introducing 2L derivatives constructed in this way. And then we can again compute this contact Witten diagram. And we find that the correlator is given by a polynomial of the cross ratio eta of degree L. So these are just warm-up examples, and they are not really interesting. The most interesting diagrams we are going to look at are coming from the exchange interaction. So we are going to consider the following exchange Witten diagram, which comes from a standard cubic interaction, and also a special one-point vertex localized on North Pole. So we are looking at this diagram here, and this diagram tells us this diagram is computed by the product of two bulk to boundary propagators, and then a bulk to bulk propagator, and we integrate this cubic point in all of this inside this hemisphere. So this is the quotient ADS. Now to compute this diagram, we can do some simple algebra, and we can show that this diagram can just be expressed in terms of similar diagrams, but in the 4 ADS space without doing the quotient. So the diagram relevant here is this one. So it's essentially the same diagram, but instead we are going to use the ADS propagators instead of the quotient ADS propagators. And also the integration for this cubic insertion point is over the whole ADS space. Now, after you do some simple algebra, you can show that this quotient diagram can be written as the linear combination of two such diagrams, where the second diagram, denoted by a bar here, is the mirror of the first diagram, where one boundary point is inserted at its inversion image. It's more convenient to rewrite this in terms of the cross ratio. Then we have W and W bar, and then this image diagram W bar is related to the first one by replacing eta with 1 minus eta. And these simple diagrams in the 4 ADS space is going to be the functions we are going to look at for the rest of the talk. And let's recall that the purpose of looking at this toy model holography is not to construct the real models and then use these diagrams to compute the correlators. And what we want is to really just to define some special functions with interesting properties. And in particular, the property we want to know is how these diagrams W and W bar decompose into conformal blocks. So the decomposition structure of these diagrams is as follows. So let's take first the exchange diagram W, and we decompose this diagram in the same channel where this field is being exchanged. So we will call that the direct channel. And we find that the decomposition involves two kinds of conformal blocks. The first, there is a single conformal block, which is called single trace by borrowing the terminology from gauge series. This conformal block has a conformal dimension delta, which is the dimension of the exchanged field. But in addition to that, there are infinitely many so-called double trace conformal blocks. These double trace conformal blocks has conformal dimensions delta 1 plus delta 2 plus 2n, where delta 1 and delta 2 are the external dimensions of the inserted operators. And these conformal blocks correspond to the operators of the following form. So these are the normal order product of O1 and O2, and with n boxes. So in the direct channel, we see two types of operators. We can also look at the same diagram from the mirror channel. So we want to decompose this in terms of these G bars conformal blocks. It turns out that this can also be done. And we encounter only these double trace operators. Now, by crossing symmetry, W bar is related to W by replacing eta with 1 minus eta. So we have a completely similar decomposition structure for these W bars. So in the direct channel, we have both single trace and double trace. But in the cross channel, we have only double trace. So this structure of these diagrams under conformal block decomposition actually has very interesting consequences. So let's first do a simple manipulation by moving all the double trace operators to the same side, and we get the right-hand side. So this equation tells us something very interesting, because it tells us that any conformal block with genetic dimension delta can be expanded in terms of these double trace conformal blocks. But note here, we need these double trace conformal blocks both in the direct channel and in the mirror channel. And since we can write any conformal block in this way, it also implies that a generic two-point function can be expressed as a linear combination of these double trace conformal blocks. So that is indicating that these guys, they form a basis. Now, notice this decomposition is different from the standard conformal block decomposition in two important ways. So the first is that in the standard decomposition, we use conformal blocks in only one channel. We either use it in the eta goes to 0 channel or eta goes to 1 channel, but we don't use both. But here it is necessary that we must use conformal blocks from both channels. And the second point is that in the standard conformal block decomposition, delta can in principle take any real values. But here, the conformal dimensions are restricted to a discrete set, which is delta 1 plus delta 2 plus 2n. So these are the two main differences from the standard conformal block decomposition. And here I also want to mention a small caveat, which is that we need to specify the space of functions so that these statements can apply. And we are going to carve out this space of functions by using the rigid behavior, which is related to eta goes to infinity. So more precisely, we are going to define the space V to be the space of functions g of eta, which goes to 0 when eta goes to infinity. And its decay rate is bounded by some negative power, where this minus epsilon, this epsilon is any infinitesimal positive number. Now, we can examine the rigid behavior of the diagrams we have already encountered. So if we consider the contact Witten diagrams with two L derivatives, since it's a polynomial of degree L, we know when eta goes to infinity, it instead of going to 0, it actually blows up. And even for the 0 derivative case where L equals to 0, it goes to constant instead of going to 0. On the other hand, if you look at these exchange Witten diagrams, both W and W bar, you see that they go like 1 minus eta. And as a side comment, so this behavior is quite similar to the rigid behavior of 4-point Witten diagrams in RD. Now, it's important that we had this condition to define this space, because this excludes the Witten diagrams, the contact Witten diagrams. This is important because these contact Witten diagrams, you can show that they can also decompose into double trace conformal blocks in both channels, and there is no single trace operator involved. So that can, in principle, cause problems, because that means that the basis we proposed is overcomplete. There are relations among these double trace conformal blocks. But by restricting ourselves to this smaller space, we don't need to worry about that, because we are not allowed to consider the relations from a function which is not part of the space. So here I'm just giving you some physical motivations to see why these double trace conformal blocks should form a basis. Maybe the argument is not very satisfactory to some of you. So in the next slide, I'm going to give a more rigorous derivation from contour integrals. But before I do that, are there any questions at this point? Okay, so let me go to the next slide, and I'm going to show you more rigorously why these double-choice conformal blocks should form a basis. So I'm going to look at the case where D is 2, and the external dimensions are identical. So we start from the standard Cauchy integral formula, where this contour here is this circle here. Now, because I assume that the functions are inside this space V, which means it goes to infinity at infinite L. So we can deform this contour to wrap around these two branch cuts from 0 and 1, which are the OPE limits. And I can drop these, the arcturn at infinity. So that gives us the following way to write this two-point function as G1 and G2, where G1 and G2 are respectively the contour integral around these branch cuts. Now this is standard. Now the next step is where it becomes interesting. So in this integral, we have this 1 over theta minus eta. We can actually decompose it into the double-choice conformal blocks. And the decomposition coefficients labeled by n, going from 0 to infinity, is some function Hn that depends on theta. So here the explicit details of this Hn is not important to us. It's just a 3f2 function. But let's insert this decomposition into the definition of G1. So G1 is this integral around this contour C1. And this shows us that this G1 can be written in terms, can be expanded in terms of these double-choice conformal blocks. So we just replace this 1 over theta minus eta by the right-hand side, and then we get some coefficients R, which are these two-point functions integrated against these decomposition coefficients Hn. And similarly, you can show that this same 1 over theta minus eta can also be decomposed in terms of the double-choice conformal blocks in the mirror channel. And we can plug this decomposition into the definition of G2, and similarly show that it can be expanded in terms of these G bar double-choice conformal blocks. So now we can conclude that this two-point function indeed can be written as a linear combination of these double-choice conformal blocks in both channels, and they indeed form a basis. So are there any questions about this derivation? Okay, so let me just summarize what we have obtained so far. So we have the following proposal for any function inside space V. The double-choice conformal blocks in both channels should form a basis. So once we have arrived at this, we can now define a dual basis for the dual space V star. And this dual basis is denoted as omega m and omega m bar. And we can always impose that this basis acts on the previous basis in an also normal way. So omega acting on G gives you a delta function, and omega acting on G bar is 0. And similarly for the other way around. But this does not completely determine the functionals. We still need to know how each omega and omega bar functional acts on a generic conformal block. So more precisely, it means that we need to know these following 4 functions for generic values of delta. But the question has really already been answered when we were looking at the conformal block decomposition of these exchange Witten diagrams. So let me now show you why that is the case. So previously we had this decomposition structure where this exchange diagram in the direct channel has a single trace operator and double trace operators, and it's double traced in the cross channel. And that gives us the following way to express these single trace conform blocks. Now we can act on these equations with the functionals. So let's act with the omega m functional on the first equation. On the left-hand side, we get omega m acting on G delta, which is exactly the thing we want to compute. But on the right-hand side, because we have this orthonormal condition, the only term we are going to get is from the nth term of the first sum. So omega m acting on G bar is 0, so the second sum doesn't contribute. And its delta function in the first sum, so we get the mth term. And this gives us the action of omega m on G delta, which is minus am divided by a. And similarly, we can act on these two equations with omega bar, and we can get all the other actions. So the message is that all these functionals will be known if we know how to explicitly compute the conform block decomposition coefficients. And in the next slide, I'm going to convince you by telling you some details of how these coefficients can be computed. Before I move on to that, are there any questions?
Yes, can I ask something? Can you explain again what you mean by single trace and double trace? I mean, from the point of view, what does this mean from the point of view of the CFT?
Yeah, sorry. So that's just I'm just borrowing this terminology from like n equals polynomials, where this here we can just understand it's like a single particle versus double particle. So here, let me go back a little bit. Yeah, right. So here, this conformal block corresponds to this exchanged field here, but these guys correspond to like these two particle states. So if you write in terms of the external operators, it's the normal order product. So like each operator O is like has only one trace. So now you take two of them, it's like double trace. Or in the CFT language, sometimes it's also called double twist operators. Does that answer your question?
Yes, it does. I'm just trying to understand what it means from the CFT point of view. Of course, I'm aware of the language from the point of view of ADS-CFT, where you have gauge series, right? And then you have traces. But here it's a bit more confusing. But thanks. I'll think about it a little bit more. Thanks.
Yeah, thanks. So really, like it's just a name. It's just a saying that this operator is associated to this field we are exchanging, and it has a conformal dimension that's tunable. And the other guys, their dimensions are not tunable. They are fixed by the external dimensions. So that's really what I mean. Yeah. So any other questions about these functionals or other things? Okay, so if not, let me move on to the calculation of these functionals. So these next two slides are going to be a bit technical, so feel free to take a 2-minute break. So to compute these functionals, we are going to use a useful trick, which is that the Casimir operator of these two particles, the two-particle Casimir, is the same as the Laplacian in ADS, which acts on this internal propagator. So by using this, so I'm going to call this combination of Casimir plus its eigenvalue to be the equation of motion operator. So it's an operator. So when we act this operator on the exchange diagram, we can use the second interpretation, which is the equation of motion in the bulk. And the equation of motion acts on the internal propagator and gives us a delta function. So that gives us the contact interaction. So you can write it as follows. So the equation of motion operator acting on the exchange diagram gives us the contact diagram, which is just 1. And this is a second order ODE for this function we want to compute. And we can solve it if we also specify the appropriate boundary conditions. And we find the solution is given by a linear combination of 2f1 and 3f2. And from this solution, we can easily read off the decomposition coefficients in the direct channel, namely the coefficient A for this dimension delta operator, and also this AN for these direct channel double trace operators. Now the cross channel is a bit trickier, but again, we can use this operator. So the observation we need is that this operator acts on the cross channel conformal block based on 3-term recursion relation. So the action give us back the original conformal block, but also 2 more conformal blocks with shifted conformal dimensions. Now we can use this in the previous equation of motion identity, which relates exchange with contact. The contact diagram we can easily decompose into these G-bar conformal blocks. And when we use this recursion relation, this is going to give us a recursion relation for the decomposition coefficients Bn. So explicitly, the recursion relation takes the following form, which involves 3 terms in general. But when n equals to 0, the first term is gone, and it has only 2 terms. And the initial data we need to input is just the B0 coefficient. And this is given by the exchange diagram evaluated at eta equals to 1. So anyways, the message is that we have a recursion relation we can efficiently solve, and we know the initial data. So by doing this, all these functionals I showed you earlier here has now been computed. Okay, so that was some technical discussion, but now let's get back to the main line of the talk. So we have obtained all these functionals. Now we can act them on the Croton equation, and this is going to turn each conformal block into a number, which is the action of these functionals. And from that, we can extract the constraints on the CFT data as sum rules. Now, here's something I want to emphasize. So in our derivation, we use the help from holography. But the important thing is that these results, the sum rules and functionals, they are valid even if the theory has nothing to do with holography, and it's valid non-perturbatively. And they can be applied to any theory. So as an application, I'm going to show you how to solve a model which has nothing to do with holography. So the case is 5 to the 4th theory, but now on RPD. And I'm going to look at this theory in 4 minus epsilon dimensions. And I'm going to solve the 1-point functions to epsilon squared power without using Feynman diagrams. So the correlation function we are considering is the 2-point function of phi. And the crossing equation looks as follows. It involves the identity operator and these double trace operators. Now we can expand the dimension of these double trace operators in powers of epsilon. And these enormous dimensions are denoted as eta. And the contribution is also expanded in powers of epsilon. Also for the external operator, we expanded in epsilon, and it's well known that the enormous dimension kicks in only in the 2nd order. Now the idea of this calculation is that we act on this crossing equation with these functionals, and then we get sum rules, and then we solve these sum rules in epsilon expansion order by order. Now, a very useful fact here is that the spectrum we start with is a double trace spectrum, And we, from the also normal property we imposed, we know that this is going to be very convenient because it is going to introduce a lot of zeros on the spectrum. So that will truncate the sum rule to only finite many terms, and that allows us to solve it. So we first start from the zeroth order term, and we act with the omega m functional. And we find that the sum rule is very simple. It involves only 3 terms. So you have contributions from the identity operator on both sides. And then there's the nth double trace operator, which contributes in the direct channel. And you can solve this sum rule, and you find that these contributions is only non-zero when n equals to 0, namely just 5, 5, you have no boxes. And this is indeed the correct answer we expected from the mean field stereo correlator, which has this following form. Now let's move on to the first order in epsilon. And we find the following sum rule. And again, we can solve it. And we find a very nice structure, namely the contribution is only non-zero for 0 box and 1 box. And for n greater than or equal to 2, the contribution is 0. And this has a nice consequence. It means that at the next order, there will still be only finitely many operators contribute in the sum rule. So indeed, at the epsilon squared order, we get this more complicated sum rule, but it's still finite. And we can solve it, and we find these one-point functions in terms of the bulk data as follows. Now we can try to do an estimate for the 3D Ising model on P3. We just need to set epsilon equals to 1 and use the bulk dimensions from the numerical bootstrap. And we find that these one-point functions are given by these values. And they can be compared with the bootstrap estimate by Nakayama. And you can see these numbers, they agree quite well. And here I want to emphasize again that this bootstrap method here uses this Gliozzi type bootstrap, which is not like the usual bootstrap bound we are familiar with. It's not a rigorous estimate. Okay, so that's epsilon squared order. In the next order, we run out of luck because now all the operators contribute, and the sum rule no longer truncates to finite many terms. So it's not clear how we can solve these sum rules analytically. But nevertheless, these sum rules are still going to impose non-trivial algebraic relations for the CFT data. So I already discussed the RPD case. Now let me spend a little bit of time to talk about the BCFT case. So there is a similar approach for the BCFT two-point functions. And we also find that there is a basis of functions and functionals labeled by the mean field theory spectrum of these double trace operators. So for example, we can consider BCFT mean field theory with Neumann boundary condition on the boundary. And we can consider the two-point function of this mean field theory and then decompose it into conform blocks, both in the bulk channel and in the boundary channel. In the bulk channel, we find operators from these double trace operators, which are made of phi, phi, and a box and n boxes. In the boundary channel, on the other hand, we find operators which are the bulk operators restrict to the boundary, and we can act with derivatives which are perpendicular to the boundary. So these operators are the analog of double trace operators we saw in the RPD case. Now it turns out if we specify the space of functions by imposing certain boundariness requirements in the rigid limit, we have a basis which is given by the conformal blocks associated with these operators. So we have these conformal blocks in the bulk channel associated with these operators, and also boundary channel, we have these conformal blocks associated with these operators. The difference is that in addition to these boundary double trace conformal blocks, we also have their derivatives with respect to the conformal dimension. And the reason that these derivatives arise is because we should view that as a degenerate limit of two towers of these double trace operators. So we have one tower from each external operator. And when we take these operators to be the same dimension, we need to take a derivative so that the number of bases remains the same. But anyways, so these double trace conformal blocks gives us a basis and we need both channels. And we can define the dual basis by requiring them acting on this basis in the orthonormal way. So the statements I made in the previous slide can be arrived by also looking at a similar toy example, toy model of holography. So let's consider the following toy holographic BCFT. So here we have this RD where it terminates on a boundary, denoted by this gray line here. And we can extend this RD space with boundary into ADS, where this boundary now becomes ADSD subspace inside of ADSD plus 1. And we are going to impose that fields living in this ADSD plus 1 space should satisfy Neumann boundary condition on this ADSD subspace. And we can again obtain the propagators by the method of images, and also define exchange diagrams of the following two types. So we have an exchange in the bulk, and we have an exchange that lives only on this ADSD subspace. So these Witten diagrams remarkably also have the same decomposition structure under the conformal block decomposition. So these Witten diagrams, we can see that in the direct channels, they have single trace operator and also double trace operators. And in the cross channel, we have only double trace operators. So by running the same argument, which is just to move the double trace to the other side, we can see that any genetic conformal block can be expanded in terms of these double trace conformal blocks. And that gives us a reason why these double trace conformal blocks should form a basis. And moreover, the action of the dual functionals can just be read off from the decomposition coefficients. So before I conclude, are there any questions about the BCFT case? Okay, great. So let me now wrap it up. So in today's talk, we introduced some general analytic approach for two-point functions of RPD CFTs and BCFTs. And we used the holography as a tool to identify a useful new basis for decomposing the correlators. And this new basis is closely related to mean field theory. It's discrete in conformal dimensions, and also it must involve both channels. And the dual of this basis is the dual of a basis of functionals. And we can get the action of these functionals by looking at the conformal block decomposition coefficients of exchange Witten diagrams in this holographic model. And acting on the crossing equation with these functionals we obtained, we can systematically extract the constraints on the CFT data as sum rules. And these sum rules are particularly simple to solve if the spectrum is very close to the mean field theory spectrum. And therefore, they are very efficient tools for doing perturbation theory around the mean field theory. Now, I also want to emphasize again that this construction, although it's very closely related to mean field theory, but the functionals and sum rules we obtained are non-perturbatively valid. And also, let me quickly mention something what I didn't mention, but it's simple to derive using the results we introduced in this talk. So the point I want to make is that the exchange diagrams we saw earlier in both channels, they together also form a basis of expansion. So in the RPD case, instead of expanding the two-point function in terms of conform blocks, we can replace the conform block with the exchange diagrams in both channels, symmetrized or anti-symmetrized. And this is also a valid expansion. So this expansion is very similar to the expansion Polyakov introduced in the 70s. And this basis also re-emerged later in these mailing bootstrap papers. Now in the future, it'll be very interesting to explore more applications of these functionals and obtain more analytic results. And an interesting generalization of what we've done here is to consider spinning correlators. And that will allow us to consider the interesting case of the two-point function of the stress tensor. So this correlator is present in all local CFTs. And I should also mention that the approach presented here is closely related to the functional bootstrap approach of 4-point functions in CFTs on RD. And recently, it was shown that there's also further connection among this approach and the CFT dispersion relation and the non-perturbative mailing amplitudes and mailing space sum rules. So it would be interesting that in the future, we can similarly consider the other two corners in the setup we considered here. And finally, another interesting and somewhat similar case is the two-point functions in thermal CFTs, which are obtained by dimensionally by compactifying the theory on the circle. So in that case, the two-point function is also non-trivial in the sense that it's not fixed by symmetries, and also new CFT data can enter in the one-point functions. But the difference is that in the thermal CFT case, the spinning operators can have one-point functions. And also the two-point function has two cross ratios instead of just one. So it's a bit different, but still it'll be very interesting to see in the future if the techniques we used here can also be useful to study that problem. So with that, I'm going to stop and thank you very much.
Thank you very much for the very nice talk. So any questions from the audience? So is there a way to replace RPD with like a length space in all dimensions? So these are different finite quotients of spheres.
Yeah, it's an excellent question. It's very interesting, but we didn't think much about it. Yeah, I think we should try to think along that line. Yeah.
So to answer correctly, that it's kind of important that this Z2 quotient is carried out by a conformal transformation. Or this is something that is not so important.
It's sorry. What do you mean by carry out by?
So this Z2 action on the D sphere, is this carried out by a conformal transformation?
Right. So this Z2 action is right. So this breaking of conformal symmetry is essentially just introducing a local point inside of ADS. So you can even forget about this quotient; it will still have this same broken symmetry.
I see.
So this is also kind of related to this like bulk reconstruction, this HKLL bulk reconstruction.
Maybe a question related to this. So this Z2 action on the ADS will have a fixed point, right?
Yes.
And then will there be a family that is obtained by deforming this fixed point, like blowing up with some size of the resulting mid-dimensional cycle?
Yeah, I think that's a fantastic question. And I think that's probably what's going to happen, like in like more realistic models, like these top-down models, because I think this fixed point, the singularity, is going to be a bit problematic for like a full-fledged theory. But I think in the literature it has not been considered like like supergravity background for like DO2n equals polynomials with the C2 quotient on RPD.
Mm-hmm.
So I think in the future it'll be very interesting to do what you said, to construct such supergravity background and do like more top-down holography.
Yeah, I see. Thank you very much for the answer. So any questions from the audience? So if not, let's thank Xinan again for the very nice talk.
Thank you so much.
Thanks.
Thank you very much.